Now here's an interesting example. We're going to find the points on the sphere of radius 6 centered at the origin, so that would be x squared plus y squared plus z squared equals 36, that are closest to and also farthest from the point 1, 2, 2. So that's somewhere inside that sphere, because the sphere has radius 6. I assume it is. You see square root of 9, yes. That's 3 square roots of 3, and that's less than 6. Okay. So instead of using the distance formula with this ugly square root, which is really ugly, we're going to have the same effect by finding the points where the square of the distance is maximized and the square of the distance is minimized. And so we'll try to maximize d squared and we'll also try to minimize it. X minus 1 squared plus y minus 2 squared plus z minus 2 squared, which is just the distance formula applied to this point 1, 2, 2. So this is our function we're trying to maximize and minimize, the distance function from a point on the sphere to that point in space. And we're subjected to the constraint that it's got to be on the sphere, so x squared plus y squared plus z squared equals 16. Using del f equals lambda del g, we get this equation. By the way, del f is 2 times x minus 1I plus 2 times y minus 2j plus 2 times z minus 2k. I hope that's obvious. Our 2 lambda del g, well, del g is 2xi plus 2yj plus 2zk. So that would make that 2 lambda x for I, 2 lambda y times j, and 2 lambda z times k. And so our 2 times quantity x minus 1 is equal to 2 times lambda times x. So in other words, lambda minus 1 equals lambda times x. Lambda minus 2 you can see is lambda times y, and z minus 2 equals lambda times z. I think you can see why that has to be, because this equals this, and you can cancel the 2's. Solving each of these for lambda, we get x minus 1 over x is lambda in this one. We would get y minus 2 over y equals lambda in this one. And z over z, wait a minute, we're solving for lambda, so z minus 2 over z would be lambda in this one. And since they all equal lambda, then they're all equal to each other. And looking only at the first two parts of this, we can see that y times x minus 1 equals x times y minus 2, which doesn't really help much. But now when we multiply that out, we get xy minus y equals xy minus 2x. And if we subtract that xy from both sides and multiply the result by negative 1, we get y equals 2x. So that was good to know, that y equals 2 times x. So looking at the first and third side, that's this one and this one, we can similarly see that z equals 2x same way, right? If this equals this, then you could solve that and get z equal to 2x. So substituting those back into our constraint equation, we get x squared plus y squared, but y equals 2x, plus z squared, but z equals 2x, and that's equal to 36. So solving this, we get x squared plus 4x squared plus 4x squared, so 9x squared equals 36. That means x squared equals 4 and x equals 2, or x equals negative 2. So x equals 2 would lead us to the point, keep in mind y equals 2x and z equals 2x, so we'd look at the point 2, 4, 4, while x equals negative 2 leads us to the point negative 2, negative 4, negative 4. Note that f of 2, 4, 4 equals 9. Keep in mind, I forgot what my f was, hang a minute. Oh, f was this, okay, so with 2, 4, 4, that would be 1 plus 1 squared plus 2 squared plus 2 squared, so that's 9. And the minimum square of the distance well, that's the minimum square of the distance, and f of -2, -4, -4 is 81. Let's see why that's so. Time out. I want to go back and look. -2 minus 1 is -3 squared, which is 9. -4 minus 2 is 6 squared, which is 36. And -4 minus 2 is another -6 squared, which is another 36. So 36 plus 36, which is 72 plus 9, makes 81. And so that's the maximum square of the distance. Then the closest point on the sphere is the point, on the sphere to the point 122 is the point 244. And the farthest point away from the point 122 is the point -2, -4, -4.